We're going to move on now to study probability. Why? Because social research usually involves sampling of some kind. And probability is important because it allows us to determine how likely it is that the sample we analyze is representative of the population that we draw that sample from. So let's consider a normal six-sided die. What's the probability that we roll a 2? If you guessed that the probability of rolling a 2 was 1 over 6 or 1/6, then you're correct. The probability of rolling any face is 1/6. What's important to understand here is that we accounted for every possible outcome that could occur when we roll a fair six-sided die, and that all of these probabilities add up to 1. 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 equals 1. We can't have a probability of greater than 1, and we can't have a probability of less than 0. There's no such thing as a negative probability. Let's go over a couple of simple rules about probabilities. How about the probability of rolling a 1 or a 2 or a 4? Or probabilities follow what's called the addition rule. You add up the probability of each event independent of the others, and that gives you the probability of producing any outcome. Let's change things up a bit and consider a standard pack of cards. What's the probability of drawing a queen of diamonds from a standard pack of cards? Well, there are 52 cards in a standard deck, and there's only one queen of diamonds. So the probability of drawing a queen of diamonds is 1 over 52, or 0.0192. It's useful to know, by the way, that since there are 4 queens in a standard deck of cards, the probability of drawing any suit of a queen is 4 divided by 52. Okay, so we've drawn our queen of diamonds, and our deck now looks like this. What's the probability of drawing an ace of spades? Well, the probability of drawing an ace of spades, if we fail to return the queen of diamonds to the deck of cards, is now 1 over 51, since there are now only 51 cards in the deck. Of course, if we put the queen of diamonds back into the deck, then the probability of drawing an ace of spades is 1 over 52. Let's take a look at something called the multiplication rule. Determining the probability of 2 events occurring together follows what's called the multiplication rule. To find the probability of 2 events occurring, we have to multiply the probability of one event occurring by the probability of the other event occurring. I've done that in 2 ways here, once with replacement and once without replacement. You'll notice that the 2 probabilities differ by only 1/100,000th. For small samples drawn from relatively large populations, whether you replace or you don't replace doesn't make much of a practical difference. Okay, let's move back now to our familiar set of scores. Let's say we're using a protocol of some sort to score children's level of aggressive behavior. The scale is a 7-point scale in which we'll assess each child in an elementary school class. We did our observations. Here are our results. On the left-hand side is the raw data, and on the right-hand side here is a frequency table showing the number of children who scored in each different level. We can look at the same set of scores in a histogram in addition to looking at it in a frequency table. If we were to select a case at random, what's the probability that the case that we select would be one where the observer scored the child a 2? Well, you can take a look at that. There are a total of 9 scores. Only one child scored a 2. So the probability, it's very similar to our dice example, the probability is 1 out of 9. What about the probability that a child scored a 3? Well, you can see that there are 2 children who scored a 3, so the probability there would be 2 out of 9. I've illustrated those probabilities over here. You can see that the probability of selecting a child who scored a 4 is 3 out of 9, since there are 3 children who scored a 4, and we have a total of 9 cases, so 3 over 9. What about the probability of selecting a case where a score falls below a 4? How would we figure something like that out? Well, it would be the sum of the number of children who scored a 2, one child, and the number of children who scored a 3, or two children. So the number of children who scored below a 4, just to follow our addition rule, 1/9 plus 2/9 equals 3/9, or a probability, or if you prefer, a proportion of 0.333. Okay, let's take a look at another one. How about the probability of picking a child who scored a 4 or above? So in the previous example, we had below a 4. Here we have a 4 or above a 4. And I'm sure you can do this very quickly just by looking at it. We have 3/9 plus 2/9 plus 1/9, yielding a probability of 2/3 or 0.667. And we'll do another one. How about the probability of selecting a child who scored either a 4 or a 5? And again, the answer is very simple. These basic principles are the same regardless of how large a sample we draw. Although I made up the previous example, many of the things we studied have a similar bell-shaped distribution. Most of the observations cluster around the mean, and the further away from the mean a score is, the less likely it is. In a normal distribution, what's the relationship between a mean and a median? They're the same. So half the scores will be above the mean and half the scores will be below the mean. Let's say we're looking at a set of SAT scores. The mean SAT score is 1,000. It's actually a bit higher than that. But just as we did in the simple example before, we should be able to determine the proportion of students who got a score of, say, below 800. And that's illustrated here in this histogram. We can simply count up the number of bars and the number of cases in each bar. And I've estimated here that about 15% of the students who took the SAT wound up getting a score of 800 or below. Now this works fine when you have a discrete set of categories. But what if we're interested in something more precise? What if we're interested in something that's measured on a continuous scale? A continuous scale is what again? It's a scale where there's an infinite number of possible values between any two values. So your height, for example, is measured on a continuous scale, because although we may not have a ruler that measures down to the level of nanometers, in principle such a measurement is possible. The number of children you have, on the other hand, is something that would be measured on a discrete scale, since you can't have any fractional children. You either have one child, either have no children, one child, or two children. You can't have 1.5 children. So if we had to measure on a continuous scale and put together a similar histogram, it would look something like this. The vertical axis shows the number of observations at each point. The horizontal axis shows the score. And for a variety of reasons, we're going to display these scores as z-scores. So far, so good. If you followed along, I don't think there's anything here to cause you a problem. But how do we find this red shaded area on a histogram such as this one? Unlike the case with discrete data, we can't just count the number of scores in each category. In other words, there are no categories because the distribution is continuous. Since we've labeled the x-axis using units of standard deviation, let's start out by determining the percentage of scores below 1 standard deviation below the mean. I've marked that here so you can see it. Remember, we can express this either as a percentage of scores or as a probability that a score will fall below 1 standard deviation below the mean. One of the most important properties of the normal distribution is that it can be shown that about 34.1% of the scores will fall between the mean and 1 standard deviation below the mean. Because the distribution is symmetrical, we can see that 31.4% of the scores will also fall above the mean. that is, between the mean and one standard deviation above the mean. Another important result of the fact that the distribution is symmetrical, as we've already said, is that 50% of the scores will fall above the mean, and 50% of course will also score below the mean. Combining this with the 34.1% of the scores that fall between the mean and one standard deviation below the mean, we can compute the percentage of scores that fall below one standard deviation below the mean. It looks something like this. We have 84.1% above one standard deviation below the mean, and 15.9% below one standard deviation below the mean. We can also show that 47.7% of scores will fall between the mean and 2 units of standard deviation above or below the mean. This leaves 2.3% of the scores in each of the two tails beyond 2 standard deviations from the mean. Similarly, it can be shown that 49.9% of scores are within 3 standard deviations of the mean, leaving only a tiny 0.2% in each of the two tails. Let's take a look now at a somewhat more difficult problem. Knowing what you know so far, can you compute the percentage of scores that are greater than 1 standard deviation below the mean and less than 2 standard deviations above the mean? This would be the area in here. We have 34.1% of the scores between 1 standard deviation below the mean and the mean, and we have 47.8% of the scores between the mean and 2 standard deviations above the mean. If we add these together, we can say that 81.9% of all the scores fall between 1 standard deviation below the mean and 2 standard deviations above the mean. Okay, to summarize then, we can say that the probability that any case we might select falls within 1 standard deviation on either side of the mean is 34.1%. 2 standard deviations on either side of the mean, 47.7%, and 3 standard deviations either side of the mean, 49.8%. And it's important to remember that the total area above or below the mean is 50% of the area under the curve. This is all well and good, but what do we do when we're asked, say, what percentage of the scores are above some fractional z-score? The problem, in other words, looks something like this. The proportions just shown in these other examples were derived from some pretty advanced math using a very frightening formula. Fortunately, a computer or even your phone can compute these proportions for any z-score. There are a number of online calculators available, and I happen to like this one. You can go ahead and click the link. Just bear in mind that this formula does not require that you compute z-scores. If you enter the mean and standard deviation of the raw scores, it will convert them to z-scores in the background for you. We're looking for the probability of getting a score greater than z equals 0.22. So you have to tell the calculator that the mean of the distribution is 0 and the standard deviation is 1, since these are the mean and standard deviation for every z distribution. After the video is over, you should go and try other z-scores at this link just to get an idea of how the calculator works. On an exam, however, you can't use the calculator. You have to use a table to look up these probabilities. This table is a screenshot that was taken from the back of your text, and it's one of the easier ones to use. Column A is where you look up the z-score you're interested in. Column B shows the proportion of scores that fall below a particular z-score. Column C shows the proportion of scores that fall above a particular z-score. And column D shows the proportion of scores that fall between the mean and a particular z-score. So looking here at our z-score of 0.22, we can see that 0.5871, or 58.7% of the scores fall below a z-score of 0.22. This, of course, leaves 41.2% that fall above a z-score of 0.22, and you can just do the calculation by hand, or you can see here that the region, the number of scores between the mean and the z-score of 0.22 is 8.7%. This ought to give you enough information to solve a whole bunch of problems, both in the homework and on an exam. And it's really important that you understand how to use these tables correctly and how to compute these z-scores properly. Let me give you some guidelines for solving these kinds of problems. Let's assume that a question asks you to compute the proportion of scores that lie above a certain score. Well, the first thing you need to do, of course, is to compute the mean of that distribution. You then will use that mean to compute the standard deviation of the distribution, and then you'll use the mean and the standard deviation to find the z-score for the raw score that you're interested in. Next, and this is really important, draw the distribution labeling the mean and the z-scores you just computed. It's critical that you draw an arrow to indicate whether the problem asks for the proportion or probability above, below, or in between two scores. It's really easy to make a mistake here and report the probability that a score is above a certain score when the question asks you to report the probability that a score is below a certain score. So it's really important to draw those arrows in. Once you've done that and you have a diagram, you can compute the area under the normal curve using the tables or the online calculator. My suggestion would be that in a homework, you try to use the table and check your answer against the calculator. The calculator gives you a really quick way of understanding the relationships between these scores and the probabilities of landing on a particular score. In terms of solving actual problems, either the calculator or the table will suffice. Okay, that's it.